Hi, welcome to Lesson 4, Quantum Error Correction and Noise Mitigation. This is where quantum computing gets real. Until now we've worked with perfect simulators, but real quantum computers are incredibly noisy. Together, we'll bridge the gap between theoretical quantum algorithms and practical noisy hardware. So we'll learn to model realistic quantum noise, implement error correction codes, and use advanced mitigation techniques with Qiskit. And this is the foundation that will enable fault-tolerant quantum computing. Okay, so understanding the quantum noise are going to require this set of installation requirements, and we are also import these libraries. You can always have it in the notebook, in the repository, and then you need to take into account that we have three types of quantum errors. I'm going to classify it in these three categories: coherent errors, incoherent errors, and correlated errors. The coherent errors are systematic errors that you can get as calibration drifts, which are seen as over on the rotation errors, gate parameters that are slightly wrong, crosstalk, which is unintended interactions between qubits, and control errors, which is imperfect pulse sequences. And then you can get the incoherent errors, which are random. This can you name it as T1, T2, which are decays on or dephasing, amplitude and phase dampings, which are related to energy loss to the environment and loss of the quantum coherence when the phases are misaligned with the rest of the system. And the thermal noise is going to impact these two as random thermal fluctuations, but also as an incoherent error, you can consider measurement errors, because also measuring can be an imperfect situation, and you can get what I call here imperfect state discrimination. And correlated errors are related to crosstalk-induced correlations, neighboring qubit interactions that are not desired in our system, and common mode noise, which are environmental fluctuations affecting multiple qubits, and control line coupling, which are shared control electronics error that comes from the system, more from the classical system that you already have. The mathematical part of the quantum noise, you can define the amount of quantum noise describing the quantum channel as the trace, the complete positive trace preserving map that transform density matrices. This is very important that when you include noise, you create a more general concept that using the wave function. The wave function is the one describing the state of a qubit, but the density matrix is the one describing the state of the qubit plus the noise in the system. So this rho is going to be our density matrix, and this operation is going to measure the trace of this matrix, positive trace preserving maps, and depending on this, you can estimate the amount of quantum noise in your system, being K the cross operation that satisfies this relationship. Here I'm just leaving you some explanation of the different types of quantum noises that I kind of already explained before, but I can define it as these five. You can check more the details on the math here, but we have these five, which are the polarizing noise, amplitude damping, phase damping, thermal relaxation. Thermal relaxation is a very specific one, comes from the physical origin of the system, that it's finite temperature environment where you can get state 1. Remember, that's a higher energy state that can just decay to a zero level, ground state 0. So you're losing energy, and this energy can be emit as light, as heat, as any kind of energy, and it's also related to the thermal fluctuations. And this is as mathematical model, is a calibration of the thermal state when the temperature goes to thermal equilibrium. The parameters of T1, T2 we're going to use later, and gate time temperature are very important here, because thermal relaxation is going to create amplitude damping as T1 decay, and T2, this time is going to describe the dephasing, the loss of quantum coherence, and also the time that the gate takes to apply the process or to be applied into the quantum system. All of these correlated to temperature are going to give you a thermal relaxation statistics, and these effects is a combination of the amplitude and phase damping. In a realistic perspective, the model's actual superconducting qubit behavior, they can be affected quite easily by these temperature differences. And also we can have the readout errors, which are also physical origin, which comes from the imperfect state discrimination when you create mistakes when you read the qubit itself, and also if you have dynamic circuit which depends on these readouts, you can then create wrong operations. And the mathematical model comes from the classical confusion matrix of any system, and you can define these probabilities of measuring in this confusion matrix as the probability of measuring 0, 1 is 1, and the probability of measuring 1, 1 is 0. And the effect is measurement outcome flips. The mitigation here is readout error correction matrices, which is easily. And then we can come here to creating a realistic noise model. Here in create realistic noise model, we're going to set different circuits, but before we're going to set the different errors that we're going to include. For that, we're going to use noise model as noise model. We're going to initialize the noise. We're going to add 4 types of noise, which ones are single qubit gate errors. Here you are going to define the depolarizing error for a single qubit gate as 0.1% error rate. You then use the polarizing error method where you define the error rate, the single qubit error rate, and the amount of qubits, which is 1. To add the common single qubit gates, this is like the standard set of gates that you can have in Qiskit. We are going to add them all. You use these 4 to add all of them into the noise model with this method add all qubit quantum error. Notice that we put the single qubit error and the gates, which are all of these ones. And then you can then have the 2 qubit gate error with a 1% error rate. We define 1% error rate for 2 qubit gate errors because due to entanglement and the way the gates operate into 2 qubits, the error is usually higher, and this is according to some of real computers from IBM that they have this error. Notice it's 10 times higher than for single qubit gate errors. You just add it as the same as the polarizing error, where you use this error rate and explain that it's going and add 2 as the number of qubits. You can add the gates that we're going to use for this kind of error, and we're going to apply 2 CNOT gates. That's why we added CX. It's not going to be for these gates, because remember that these gates are for single qubits. Then you can have this third error, which is going to be thermal relaxation. If you remember, we needed some parameters for this kind of error. We have T1, T2, gate time, and temperature, being the decay, amplitude time, and the dephasing damping too. We're going to set it as some physical parameters that are quite close, standard, as 50 microseconds and 70 microseconds. And the good time from gates to apply in superconducting qubits using as just for example, it's 100 nanoseconds for the gate time here. So that's why we set this number. You anyway can play with these values, but this is like going for standard computing. And the temperature in this system for superconducting qubits usually is low temperature, around 50 millikelvin. one important fix here is that you cannot use this directly. So we're going to import thermal relaxation error that comes from this model of errors from Qiskit error, and we're going to create the relaxation error from this method, adding these parameters, and we create this object that contains the model that we can add directly as error for qubit quantum error. We're going to then add the thermal error as before, the gates, all the gates, and we are going to set false because we're managing multiple channels, and then this is how Qiskit do not give us alarms that we don't need right now. If you check here, then we also add the readout errors. We define then the probabilities of measuring 0 when preparing 1 or measuring 1 when preparing 0. We define it as 2% and 1% as asymmetric readout errors. And we define and we create this matrix, the confusion matrix of the readout error. And again, as the same one, we can use readout error as method to create an object that Qiskit can read, which is added here in noise model with the method add all qubit readout error, and just add readout error. We don't need to define for this kind of error any number of qubits, because it's a single qubit type when you measure the qubit itself. And then you have here the list of models. So to demonstrate the impact of this noise, we set 4 different kinds of circuits. The first one is going to be a simple single qubit circuit. You have quantum circuit with 1 qubit and 1 classical bit. You just apply a Hadamard gate to this qubit and you measure it. We're going to name it simple H. We're going to add it into this list of circuits. For the next one, we have the bell state preparation that you can know that is just 2 qubits, 2 classical bits, and applying the Hadamard gate and the CNOT gate to the qubits to create an entanglement state. You measure it and then you store it. Then the GH set state is the extension of the previous one for 3 qubits. Then you also add 3 classical bits. And you apply Hadamard gate and 2 CNOT gates to 2 couples of the qubits. You measure it and you get and you store it into circuits. And to the end, I wanted to add deep circuit as a many gate system, where if you check, we only have 2 qubits and 2 classical bits, but we have 10 layers of gates. In this 4, we apply this operation 10 times, which is a lot more of gates than in the previous ones. We created entangled states with the Hadamard gate and the CNOT gate, and we apply also our extra rotation to the qubit, to both qubits, set rotation to 0, to the qubit 0 and the qubit 1. We measure it and we store it as deep circuit. We're going to then create the simulators. The only difference is that the ideal simulator goes as IR simulator, and the noisy simulator goes as IR noisy model equal to realistic noise. Here in this one, we're going to add the realistic noise. What we can expect is that the chances of shots are going to vary a bit, and more the error you have and more the states you have, you're going to get a larger difference. This is just to print out the results, and you have this method here to estimate the fidelity of the ideal circuit with the noise model circuit. And checking here at the end, the noise impact demonstration, you have the summary of the results. Check the simple H have quite close results. It's a small error for the single qubit, so of course you just get 0.9993 of fidelity, which of course you can, if you play with the error rate, you're going to vary a lot this result. Checking the test bell state, the error is larger, and check why. You have that a 50% chance of both being 1 or both being 0 of the qubits, but when you have noisy results, you get extra states. The probability that you have in these two states is diffused into other states, and that's why you have a result of 22 shots of the 1-0 state and 23 shots of the 0-1 state, which is something that is not supposed to happen, because in the way you create a circuit, you do not have these states. You're not supposed to measure these two. And something similar and in a larger scale, you can see it when you have 3 qubits. With 3 qubits, you in the entangled GHZ state, you are supposed to get all of them as 3, as 0, or all of them as 1. One detail here is that you get all of the combinations. Notice that the ones with the small values are the states that you don't want. Here you have 14, here you have 10, 11, 5, 10, and 10. And these states are not supposed to be there, but because the noisy results, the damping and the dephasing misalignment of the qubits, the probability of the first 2 states that you want diffuses into other states, and then you get different results. And this one is the one with the lowest fidelity, because the quantum operations into 2 gates have larger errors than for single qubits. And one interesting thing is that if you test the deep circuit, notice that it still has the highest fidelity, even though you applied a lot more of gates. Notice that it's 31 of depth of the circuit, and you have 43 gates in this case. But still, even if you have difference in the measurements, and you have difference on the states that you are supposed to get from the noisy results, you still have a larger fidelity, because it's not all depending on the amount of gates that you have, but also in the gates that you use. It depends on how is your circuit designed. So if you have more 2-qubit operations, you're adding more noise, but also depending on how you add those gates, you can decrease or increase your fidelity to the ideal result. Taking this into account, then you need to apply some correction, and then I want to discuss a bit what's a quantum error correction fundamental. So you have 4 key principles. One of them is the redundancy. Usually what you're going to define as one logical qubit is a codification of n physical qubits. With a bunch of physical qubits, you're going to define a logical qubit. So in case one of these physical qubits have some error, you still have an average of what's the logical qubit. And the syndrome detection and error correction are going to be the process where you measure the error syndromes of the system without disturbing the data, and apply the correction based on the syndrome results. And the fault tolerance are errors in correction that don't spread to data. To get more close to this, I leave you this as details of the quantum error correction principles as the challenge, where you have non-cloning theorem, you cannot copy quantum states, measurement destroys superposition, continuous errors, and versus discrete classical errors. You also need to correct the data without looking at the data. The solution is what we call stabilizer codes. One of them is the logical qubit. We also have stabilizer operators that commute with logical operators, and this measures stabilizers to detect errors, and these are the syndromes. You are going to see what are the kind of errors that you usually have in your system, so you can apply the correct operations. Here I leave you some formalism, but let's go directly to the implementation of the 3-bit flip code. Here I'm going to use this create 3-bit flip code method to explain it. Okay, here we need to implement the logical state of 0, 0, 0 and 1, 1, 1. So the 50% chances of getting all of them 0 or all of them 1. In this implementation, we need to add extra qubits to protect against the single bit flip in this case for the X operator errors, and we're going to use these operations to the qubits as stabilizers. We're going to be able, the definition of distance equals 3 means that you have one error correction with 2 syndrome qubits. At the end, we're going to have here in the method, in the class 3 qubit with flip code. We initialize it with the data qubits that we have, that are 3, but we're going to add 2 ancilla qubits, which are the syndrome qubits. At the end, the total is gonna be 5. And then in this method encode circuit, you can encode your circuit with the total number of qubits and some of the ancilla qubits for the with the same number as the classical bits that you're going to use, because the ancilla qubits that you're going to have are the ones that you're going to measure, so you can identify the syndrome, the error that you're having in your system. To encode the logical qubit 0 into a physical qubit 0, 1, 2, remember that we have these 3, we do these operators. So we copy the bits of 0 to bit 1 and they copy the bit of 0 to bit 2. And in this step, you're encoding these 3 physical qubits into one general logical qubit. And then we get the method of syndrome circuit, where you also create a circuit as the same as before, but measuring the stabilizer of using this operator using the ancilla qubit 3. Then you use this operation of the CNOT gate to control the data of qubit 0, and then you use the CNOT operation again to control the data of qubit 1. You're applying qubit 0 and 1 CNOTs to the qubit number 3, which is going to be measured then to check the result of these bits. For the syndrome circuit, you define it the same, but what you're going to have here is the stabilizer, set 0, set 1, using ancilla qubit 3. You're going to apply a CNOT gate with the qubit 0 and qubit 1 into the qubit number 3, so you can control the data of qubit 0 and qubit 1. You do it as well as is done here, and you measure qubit 3, so you can have a syndrome bit of 0, and then you can define the same measurement stabilizers C1 and C2 using the ancilla qubit 4. Notice that then you have the difference that you apply qubit 1 and qubit 2 into qubit 4. Here you can control the data of qubit 1 and qubit 2. All of them is getting this information into the other 2 qubits, and then you can just measure it and measure the syndrome of bit 1 for the qubit 4. And then what ancilla it's computing here is a sort of the qubits to do a parity check. In the first case, you have a syndrome bit of the same parity if you get 0, and if you get 1, you have a different parity. So you get an information that qubit 0 and qubit 1 is not the same. And for the second case, the same happens, that if you get 1, you know that qubit 1 and qubit 2 are not the same, and then you're getting some error there. And if you get that, you can identify then which ones of them are equal and which ones of them are varying. You can then localize your error. But we never measure the data qubits directly. This works without destroying the data. We only measure the relationships between them, the parities, and this preserves the quantum superposition while detecting errors. What's a full quantum circuit looks like? So we can define it as the method here, full quantum circuit. We are going to create a complete quantum circuit. First, we make the encoding. We create the error injection, where we add the error qubits. Here, we apply the X operator. X is the gate that's going to have the error. a syndrome measurement. In a real system, all of them have error, but let's assume that the CNOT gate, you know it very well. The one that you cannot control, that you already know a lot of the results and you're going to trust on the operation. But then in the syndrome measurement, as I showed you before in the two methods, the two previous methods, you're going to apply it as is presented here for the ancilla qubits 3 and 4. And then you're going to have the error correction with the proper conditional logic. We use this fixed, simpler conditional structure. Here we have these three conditions, and it's going to depend on the results of the measurement. And this is a dynamic circuit, if you remember, because we're measuring in the middle, and depending on this measurement, we're going to apply an error correction again. So you get the apply x2 if the syndrome is 0, 1. You are going to apply x0 if the syndrome is 1, 0. So you apply x to the second qubit, which is going to flip it. You're going to apply the NOT to the qubit number 0 if the syndrome is 1, 0. And you're going to apply the NOT gate to the first qubit, to qubit number 1, if the syndrome is 1, 1. With these three different combinations, you can detect which of the qubits is modified. Remember that here we're measuring 2 ancilla qubits, and that's these two, and we can detect at least one error. If we have 2 errors or 3 errors, we cannot detect it anymore. So this case is detecting 1 error with 2 qubits, with 2 extra qubits. And then if you increase the complexity of the system, you're going to need a lot more of qubits to do this correction. And as a final measurement, you just measure off the data qubits. Return then the 3-bit flip code, and then keep going here. As here I'm just presenting the scenarios and some of the running of the simulation that you already have it from the previous modules. Check here that I just summarized the results. If you check it, testing the error correction, you have non-error version, error on qubit 0, error on qubit 1, and error on qubit 2, which are for the same circuit, of course. And then you define the definition of the syndrome. For non-error is 0, 0, and any kind of error is 1, classical bit giving 1, or both of them, and then you can detect where you have the error. As a more number of qubits you have, this is going to be more complicated. So I leave you as a homework or to study this STEAM7 qubit code, which is a more sophisticated error correction code, but it's an extension of what we have just seen. It's a lot more of qubits, which is 7, and then you're going to codify 1 logical qubit into 7 physical qubits. I'm gonna leave it to you for you to check it if you want to as an extra implementation, but check that the logical operators for the correction are larger, and you're going to get a better control, of course, of the error. And this is known as a CSS code, as Calder-Bank-Shor-Stein construction, and corrects arbitrary single qubit errors for X, Y, and Z gates. It also have the distance of 3, but it's based on classical 743 Hamming code. I can leave it just for the ones that are interested in a more sophisticated version of this, but with the simple one we can just understand what we're doing here. So check for error performance analysis, correction performance analysis. We have this method, analyze the quantum circuit performance, where we're going to implement different error rates. Here I just set from 0.1, 0.5, 1 to 5 and 10% error in the result in the circuits. We're going to check the results with the uncoded bit flip tree and the perfect correction systems. So we can understand a bit more of this. Here, I'm just adding the noisy model. As you can see, we add the errors for the X and Hadamard operators. We are going to have the uncoded performance as this circuit. We're going to have the 3-bit flip coded performance as the circuit that we already defined before with non-error qubits. We're going to run the simulations with 1000 shots, and we're going to check the uncoded simulation for ideal simulation run and a noisy simulation run, right? Where we have the noise model as built before. And we are also going to use the function that we created before as calculate distribution fidelity to check the fidelity of these results. We're going to have coded simulation, which is going to assume that we have perfect syndrome measurements. Remember that you can also have error on the syndrome measurements, but that's a step forward. But a step further, but you can then get the perfect correction, which is the theoretical upper bound, and it's defined by this operation. This leads order for 3-qubit codes. But then here is just printing results, and let's check the different results that you can get here. But I prefer to, you can check these numbers by yourself. For example, for the encode fidelity, you get, when you get the 3-coded code fidelity or the perfect correction, you get 1 of fidelity. But if you don't do anything, you get a different fidelity, a lower fidelity. And then, depending on the error that you apply, you're going to get different values. 3-qubit coded fidelity always gives you the highest one because you're identifying exactly the error, but perfect correction gives some differences. But one detail here is that when you have errors that are rare, like 0.1% error, can be more costly to overhead the error correction, to overcome the error correction, and maybe it's not necessary because 0.999 maybe is good enough for this. But error correction start to help, and well, here the overhead is still minimal. When we are approaching the threshold at 5% error, which is this one here, and then for this one, we need to analyze the performance of the quantum error correction under various noise levels. We define this set of noises rates or error rates, and we're going to use from 0.1 to 0.5, 1, 2, and 5, and 10% error rates. We're going to have 3 results, one uncoded, one with the model of the bit flip tree correction, and the perfect correction, which is going to consider the theoretical best performance, assuming best syndrome measurements. Then we're going to get the here in error rate in this 4, we're going to create the errors. For an uncoded performance, we're going to use the minimal circuit to test pair performance, the simple edge gate plus the measurement. And for the 3-qubit bit flip coded performance, we can use the one that we already built on top with error qubit equals none. And then we can run the simulation with the IR simulator in the ideal way, and in the noisy simulation where you just add it into the method. And so we define 1000 shots. We're going to get here the uncoded simulation comparing the ideal and noisy one, and the coded simulation with the 3-bit flip with ideal and noisy one as well, and use the calculate distribution fidelity to estimate the fidelity of these two. We're going to also add this perfect correction, which is a theoretical upper bound. This is considering this perfect fidelity, which is a perfect correction formula where P is the error rate. This accounts for second order errors, two errors happening simultaneously, and first order errors, which is single bit flips, which are perfectly corrected. So if you check in the results of the performance, for the first case in 0.1% error rate, error correction overhead cost nothing when errors are rare. We have 1 as the fidelity for these two cases, but for the uncode fidelity is still too high because the error is small and it's a simple case. And for 1% even, that's here, it's still quite good. Error corrections starts to help because you see here that the 3-bit code flip is 1, but still the overhead is minimal for this case. But then at 5%, notice that the perfect correction, which is the theoretical one, is already decreasing, and even it's lower than the uncoded fidelity. We still have 1 for the 3-coded fidelity strategy, but the perfect correction fidelity is lower, which means that we are already approaching the threshold of the theoretical limit, right? And even if you check for 10%, the uncoded fidelity is still good because it's only 1 gate. Here we still have 1, which is amazing. And the perfect theory, because it has this second order error, it's already becoming significant. So our implementation is performing at the theoretical limit. It's already needing some extra correction. And why the uncoded stays so high? The encoded circuit has just one Hadamard gate, the H gate, and with a 10% error rate, it has 90% chance of non-error. That's why fidelity is 99%. Measurement statistics is only that. But for this simple test, error correction maintains perfect fidelity even at 10% physical error rate. But remember, real circuits have many gates where errors accumulate. So this is for the simple case. I encourage you to test this same error for the case of the 7-qubit or larger systems. We already present some deep circuits, so you can check this and see how these corrections are going to be more significant while you increase the amount of operations. And you can check here for visualizing error correction performance. All of this is just to print these results. Let's go directly to the tables. Here I leave you a lot of the code of these plots. You can get then for these 3 cases the uncoded 3-qubit code and perfect correction. Notice that it's not, at least for this simple circuit, a lot of difference in the performance versus the error rate. But in the correction threshold, the uncoded one has this behavior, while the 3-qubit code remains constant because you're perfectly correcting the error. In the resource requirement, you have a difference in the sense that in the uncoded case, you have 1 qubit and just 1 physical qubit and 1 logical qubit. For the 3-qubit bit flip, you have 3 and 3, and with the 7-qubit STEAM, you have 7 and 3, which means that you have 7 physical qubits, but you are also having 3 qubits. And the surface code with also distant 3, you can get 9 qubits encoded into 3, right? And remember that the red one here is the distance, being just the amount of qubits that you have. These physical qubits are the ones encoded into one of those 3 qubits in these cases. Just in the first case, the encoded qubit is 1 to 1, right? For error syndrome detection, if you check the first possible states when you have 2 qubits, you can check a syndrome pattern where 0, 0 is non-error, 0, 1, 1, 0, and 1, 1 are the ones with errors, and you can name it as Q2, Q0, and Q1, which means in the qubit number 2, qubit 0, or qubit 1 when you detect one of these syndromes. And the classical versus the quantum error syndrome correction. And in the classical versus quantum ECC, you get the into the classical versus quantum ECC, we can compare complexity of the classical simple error types in bit flips, high redundancy, straightforward syndrome measurement, to the quantum complex error types from the gates X, Y, Z continuous. A lower redundancy possible. It's a sophisticated syndrome measurement preserving superposition. I'm gonna leave you here just a roadmap of how the logical qubits scale over the years, or expected roadmap of that. We can have in the order of 10 power to 0 for small codes, but at least for having useful scale, we need 10 to the power of 2 physical qubits into the logical qubits. And then we then, for quantum circuit roadmap, we need some amount of. Then we need for a bit of a roadmap. Remember that you need an amount of logical qubits then, not physical qubits. For small codes, at least right now, you have the order the 10 to the power of 0 for logical qubits demonstrated. But for being a useful scale, you need at least 100 logical qubits for real applications. And the amount of qubits, the physical qubits needed for a logical qubit, it's going to depend also on your hardware capabilities. And large scale is needed at least 10,000 logical qubits for universal quantum computing. From this, let's go to advanced noise mitigation techniques. Okay, so for advanced noise mitigation techniques, we just learned quantum error using 3 qubit bit flip code, and that's powerful, but it requires extra qubits. So now we're going to try to not use extra qubits. We can imagine that you cannot afford that overhead all the time, mainly in small devices with 50 or 100 qubits. So the alternative is noise mitigation, which improves the results without needing extra qubits. Instead, you accept that the errors happen, and you use smart strategies to reduce their impact, as using a classical post-processing to fix the results. One of them we are going to present here today, zero noise extrapolation and symmetry verification. For the first one, we're going to run the same circuit multiple times, and then you're going to amplify the noise and observe the trend. And that's how you don't need extra qubits. You can just identify how the error is increasing, and then you just do a backward engineering to the data, and then reuse it. And symmetry verification is that when you know the states that you are supposed to have, you can just normalize, remove the state that you don't need, and normalize the system to get the counts that you should get for that. So here, for example, in this method, we are going to create a bell circuit as usual with 2 qubits. We know the exact answer is only 0, 0 and 1, 1, and that's what should appear with 50% of probability. And the forbidden outcomes are 0, 1 or 1, 0. So this one has a clear symmetry, even, parity only, and all the bits should be even, some even amount. And for this, the zero noise extrapolation, it works the same as if you know that you have a thermometer that has a and that it's broken and always reads an amount of degrees higher, if you measure it at different room temperatures, you're going to get a trend. You are going to see the shift of your thermometer with enough data. And here we're going to do the same, but with amplification of the noise, one time, twice, and three times noisier. And we are going to observe how the quality is degrading in this trend. And then you can just extrapolate it to the zero noise case. We cannot remove the noise, but we can intentionally amplify it. So we run the gates multiple times and measure the trend and mathematically predict the zero noise. Here in the definition zero noise extrapolation, we are going to define the circuit and the noise factors once, twice, and three times. We define the noisy model with the error rate of 1%, and then you're going to use set in the Hadamard gate. Here you can define also the 2-qubit error with the 2% factor, which is going to be the error for the C-not gate, and which you're also going to amplify 1, twice, and 3 times. We're going to use the air simulator, and we're going to apply 1000 shots. From this, we're going to get the counts, and here we're going to calculate the expectation values that we're supposed to get. We want 0, 0, and 1, 1, and then we're going to measure it. Remember that Qiskit accepts the count as 0, 0, and it's always adding this 0, 0 as the basis that you're measuring. And you're going to divide it by the number total of shots to know how good is this expectation, and you add it to the expectation that you need. This is supposed in the ideal case to get to give 1 as a result, but in the noisy case, and as noise increases, this value is going to decrease. And then for that, we're going to add this factor and the expectation into the results, and we're going to count them. And then we're going to use a linear extrapolation and see the zero coefficient. So you find the intercept, and if you want, you just need to move the intercept so you get your real result without error. And for the case of the other mitigation technique, we can also define another model with these 2 errors again, one for 1 single qubit and the other one for 2 qubits in Hadamard and C-not gate respectively. We again define to run the ideal and noisy simulation, and the difference here is that you're going to apply the zero noise extrapolation from the test circuit, and you can observe then the result of this. But for the apply symmetry verification with the proper string handling, symmetry verification is just avoiding the values that you know that you cannot have. So here I'm just testing it, and you're going to see if the parity of the result makes sense, if it's 0, 0 or 1, 1. If not, you're not going to add it. You're going to take it as a forbidden value, and you're going to skip it. And then you're going to verify the counts, the amount of counts that you get. And here in verifying counts norm, for example, if you have 80 counts or let's say 800 counts when it's supposed to be 1000, you're going to normalize that and create a transform the value of 800 to a 100%. So let's say that it becomes in a different ratio that adds at the end 100, because at the end you need more the probability than the total number of shots. I'm going to print all these results. So let's check here the results itself. From this test, circuit valve state preparation, that remember it's 50% 0, 0 and 50% 1, 1. You in this first testing of the mitigation techniques, in the ideal result you get 0, 0 and 1, 1 with some close 50% chance. In the noisy result, you're going to get extra results, extra states, 1, 0, 0, 1. Here are 17 shots that are not supposed to be there, and the noisy fidelity is 0.99. For the zero extrapolation analysis, you got again an increment in the noise. So check that for this 1-0 state, you got 7 shots, then 10, then 15. This is because the noise is increasing, so the amount of probability diffusing into those states is also increasing. And you check that expectation value is also decreasing here. Then after you perform the 0 noise extrapolation, the value is 0.99. So it's actually quite good. It's even better than the noise fidelity that we got before. So it's already, it's not too high, but this is, of course, you're going to notice it more in larger circuits, but it's still, it needs to be better than the noisy results. So this worked quite well. But for the symmetry verification, because we have an ideal symmetric bell state, we just avoid the system if you make the count of this 0011. These do not add 1000, which makes sense because we filter those results. But if you just normalize this, you're going to get a fidelity of 0.9996. It's not 1, it's quite close, but it's not 1 because some of the probability did not shift, also did not diffuse equally into all the other ones. And that's the only difference. But check that you can get a quite good fidelity just by filtering the results without any extra qubit. And that's actually something useful in the small systems where we cannot afford to have 10 times physical qubits just to create one logical qubit. As takeaways and future directions, I leave you here some of the fundamental challenges, stabilizer code frameworks, and more information that goes from the practical implementation. Here we observe the 3 qubit bit clip code, which is the simplest demonstration. This 7 qubit code is corrects arbitrary single qubit errors, but we also have what's called surface codes, which is the most promising for large case implementation, which I recommend you to check what it's about. And everything is dynamic circuits enabled in real-time error correction. That's why the last module was important to mention here. But remember that by dynamic circuit, we also meant to that we measure in the middle of the circuit, and the measurement, the outcome being 0, being 1, is going to activate or not a condition of an operation in our system. Now we have some noise characterization. We have different types of noise, and in a realistic simulation, we need to consider them. And we have an arsenal of methods as strategies to fight against the noise mitigation. And leave you also some advanced exercises for you to check if you want to. One of them is implement the 3 qubit phase flip code again from 0 and create the syndrome lookup tables for different error patterns. But even an advanced research problem is to implement a small surface code patch with full error correction. You can check it, and even you can go to design machine learning assisted error syndrome classification, which is to identify the error using machine learning, and even make more complicated analysis. So you start just classifying the error, the syndromes, and predicting it without needing to have a lot of qubits. Also develop real-time adaptive error correction protocols, implement quantum error correction for continuous variables, and so on. You can check all of this as the further steps to more complex designs. There are a lot of theoretical investigations of this, but as a conclusion for you, this goes for the fault-tolerant quantum computing, and I want you to master this part because it's critical in the understanding of quantum computation and the challenges that you get while you're increasing the systems. Everything is used in current quantum computer benefits from noise mitigations, and the connection to this course progression. Remember that we went from the quantum basics, so how protecting the quantum information, the primitives, which are like the main static base of the circuits, the dynamic circuits, and now the error correction, which is itself a dynamic circuit, because you need the measurements of the ancillas as reference to know how or identify your error. The next steps is advanced quantum algorithms, and for the next one we're going to observe these variational quantum algorithms, which are noise resilient optimizations and machine learning protocols. We're going to observe to check a bit of this. This is a broad topic, but yeah, we're going to try to take some of it. And quantum advantage applications, well, you can create now the algorithms, but we're going to try to abort these variational quantum algorithms. So thank you so much, and see you in the next lesson.